Good morning, everybody. So I'm Nicolas Long. I'm working for one of the companies sponsoring this congress here, a company called Vision Research. We belong to the Amitech group. So we have also a booth next door. So you're more than welcome to join and come and talk to us at some point during these 2 days. I'll be there most of the time. So please feel free to talk to myself or one of my colleagues. So it's a bit difficult to come after such great presentations, so I'm going to differ a little bit from the subjects that have been covered. I'm going to talk about instrumentation, which is, I guess, also one of the relevant subjects in such a congress for all of you working on research or development of new microfluidic systems. So our company is specializing in high-speed imaging, so we make fast cameras to make things simple. As such, high-speed imaging has been used quite thoroughly for many years in microfluidics. Some of you may be using, I've seen a number of nice videos in Professor Lee's presentation, for example. So many of you probably are using high-speed images already. If not, well, that's the purpose of that presentation, to get you introduced to that. And I'm also going to cover some of the new developments in that technology. So there are two main categories of applications of high-speed imaging in microfluidics. One is quite obvious, what I just mentioned, is the development and validation of microfluidics processes. So that's typically upstream in the development of new technologies, new research papers, new methods that are being developed by many of you. And of course that means that we're going to look at microfluidic processes, so we're going to just observe them to start with. That's a first step. And one of the challenges, obviously, in microfluidics is first you have to see the unseen, things that we can't see with our naked eye. That's one thing, and that's microscopy, what microscopy helps with. But you also have to look at things that are too fast to be seen. So beyond the microscopy aspect, there's also the velocity aspect, which comes with scale, and we'll talk about that in a minute. On top of pure visualization, we're also facing the challenges of measurement. So seeing is one thing, measuring is one more thing, which is very relevant in many of your applications. And there are a number of methods that I'll cover in that presentation that allow us to go further than just seeing and actually measuring different physical characteristics of the flows and the processes we're looking at. And of course, one more thing is the characterization of the particles, cells, droplets, bubbles, and other objects that you're observing and using in your processes. And we need to measure the size, shape, and other characteristics of these objects. Another second category of potential applications of high-speed imaging in microfluidics, which is a bit more recent and a bit more, or a bit less common, I would say, is the real-time use of high-speed imaging. So if some of you are familiar with machine vision, so basically cameras being used as automated quality control instruments in the industry, manufacturing industry, basically some companies are now exploring the use of high-speed imaging and high-speed cameras to perform some of the tasks that microfluidics instruments and microfluidics systems are performing. So there are things that are very similar to what you can do in machine vision at the microfluidics scale, like real-time flow measurement, real-time particle, cell, droplet, bubble characterization. So coming back to what I mentioned earlier, but this time in real time and providing even closed-loop information that can be used in an automatic process for sorting, shaping, and other aspects of that microfluidic process. So, of course, that's stating the obvious. You're looking at a very small scale. Even for a given flow velocity, looking at a small scale means the time scale is getting smaller as well. So as long as you're getting into microfluidics, you're immediately getting into small spatial scales and naturally small time scales, and that gives you a necessity to use high frame rate cameras. High speed imaging is required naturally by microfluidics. Historically, fluid dynamics in general, I'm not talking only about microfluidics, but fluid dynamics in general has been very commonly using image-based techniques, so techniques that rely on imaging and photography for different types of measurements. Of course, the first step, which is not a measurement but just visualization, is an obvious one. Seeing what is happening is the first step to understanding. There are two techniques beyond visualization that are commonly being used, and I'm just using these as proxies for many variants of these techniques. The first one is called PIV, particle image velocimetry, and this one is basically relying on a slightly higher particle density that gives you a capability to use correlation methods, so correlate images at T0 and T1 together to understand what has happened between T0 and T1, and that brings you, that's a field method that brings you a complete 2D or even 3D velocity map of your flow. And we will discuss in a minute how you do that and what that gives you. Of course, to achieve a high particle density, you need particles in the first place. You can have particles naturally in your experiment or in your system, but you can also seed your flow with particles if needed. The second technique is called particle tracking velocimetry. That's meant for lower particle densities, and that basically comes down to individual particle tracking. And when you track individual particles, they can be, again, droplet cells, particle vesicles, whatever, objects. And this is based either on correlation, just like PIV, or on other image processing techniques. Of course, when you apply techniques like PIV or PTV at the micro scale, so you can see the micro headed here. As I mentioned, you need seeding particles or you need equivalent object in your flow, and I think many of you are already quite aware of the kind of particles that can be used, but we can discuss that on our booth if you're interested in more information about the particles that could be added to your system. The result of such experiments is the kind of data that is represented here. So that's basically a map, a velocity map of the flow, so that allows you to visualize vortices and other aspects of your flow, and that's actually potentially 2D, 3D, or 4D map, meaning 2D just velocity, 2D velocity vectors like are represented here, 3D getting the third component out of plane, and 4D getting the time aspect, so refreshing that map several times per second to get, of course, a movie of the evolution of your flow along the process that you're observing. In order to get into that fourth dimension, you need to look at what is currently called in more general fluid dynamics. You need to look at time-resolved PIV and PTV. And actually, time-resolved usually means a high sampling frequency. I mentioned that you will get a refreshment of your velocity map several times per second. Typically, the aim in time-resolved PIV is to get even much more than that, more hundreds of times per second or thousands of times per second, which is relevant especially at a smaller scale, as I already explained. There are different ways to do that. There are basic ways which allow you to see fast flows and measure fast flows without refreshing very fast. I won't go into too many details here. That's called frame straddling, and you're more than welcome to come and discuss that with me. But that's not sufficient in many cases. Refreshing often your velocity map, several hundreds or thousands of frames per second or more, is very relevant in your type of application. So high-speed cameras are required in many cases to get that high-speed sampling, high sampling frequency characteristic. So yeah, that's one example of what you could do. We've just discussed quickly the applications of the slight differences between standard PIV and microscale fluidics. Let's look now at what the microscale challenges of PIV and more generally fluid measurement, fluid flow measurement are. So that's just me, not me, sorry, explaining these. This is from a paper cited here, and I'll cite two papers just as a sample of what researchers in your field are saying about the challenges of micro PIV. One thing that I highlighted here is the volume illumination effect. We'll talk about that in a second. Out of focus particles, low seeding densities. I mentioned that PIV requires high seeding densities. In your case, as you have a high magnification in micro PIV, obviously you end up with a low apparent seeding density. You see less particles per area in your image because you are already using a pretty high magnification. So apparently using the camera, you have a low seeding density. Another issue that we're going to address in a second is the signal-to-noise ratio of recording images and the signal-to-noise ratio of the processing that you apply to these images. And these are, let's say, these two groups here are the two main groups of challenges that we are encountering in image-based measurements in microfluidics. So in standard fluidics, you would use a nice expensive laser like this one, create a very nice light sheet like this, and that works very fine at a big scale, obviously, and that's very easy to achieve, or quite easy to achieve at a large scale. That's almost impossible to achieve at a micro scale. So what you end up with would be then to go into a different type of illumination, sometimes with a laser, sometimes with LEDs right now, because they are becoming a very popular and efficient way to offer lighting for microfluidics measurements. But then what you end up with is what is called global or volume illumination, meaning you actually, instead of illuminating a light sheet, illuminating a very thin part of your experiment through that laser sheet, you have to illuminate the whole experiment itself, and you're seeing a bunch of particles all overimposed, and you basically can't see anything, and you can't measure anything here. So the challenge, one of the challenges is actually to get from here to here, and to get a typical image that you can use for correlation-based image processing that gives you the velocity map we've seen earlier. One of the methods to do that is what has been applied here is confocal microscopy, and we're going to talk about that also a bit later. A second approach from a second group, that's actually quite interesting. PIV has been in fluid dynamics a very commonly used method for many, many years. I would say probably 50 years or more. And there is something called the International PIV Challenge. That's a challenge that image processing specialists are competing against in bringing the best image processing and image correlation algorithms to get good and accurate measurements in fluid dynamics. And lately, the fourth international challenge that has happened in 2016 has actually brought, for the first time, one microfluidics test to that challenge. And there's a very nice paper that I encourage you to read if you're interested in that subject that gives you the main results of that challenge. And the first case in micro PIV, the kind of opinion that was given by the scientists who were running that challenge brings us back to more or less the same issues and the same challenges. Out-of-focus particles, digital image pre-processing algorithm to enhance the spatial resolution, so we're going back to resolution, signal-to-noise ratio, and also low particle density. And one more thing that we haven't seen yet is the strong spatial gradients that I'm sure many of you are familiar with in microfluidics. So these are essential challenges linked to the micro scale. Talking about the pure time-resolved aspect of PIV at the micro and macro scales, there are other additional challenges. One is sensitivity. We have to use CMOS sensors, image sensors, at the moment at least, to offer high-speed cameras, high frame rate sensors. So CMOS sensors are typically a bit less interesting in terms of noise, sensitivity, and other aspects. And sensitivity has been a problem for a very long time, and is even a worse problem in your applications where illumination is difficult. Microscopy is not the easiest configuration, optical configuration for imaging, and that consumes a lot of light, you could say. Signal to noise ratio is another issue typical of CMOS sensors, at least historically. And one less, which is more a practical thing, but that's, practical is important, it's very important. Cameras have been very, very bulky. And that's also a problem for a reason. So we are facing a double set of challenges from a micro scale on one side and from the time scale on the other side. Still, if you look at the papers that are being published, you'll see a lot of papers are being published that mention high-speed imaging being used as a diagnostic or instrument. And I'm sure if you review the literature, you'll see that immediately. There are many reasons for that. I won't go too far in that, but basically, seeing is believing. The pure visualization aspect is key and has been key in fluid dynamics in general for you could say, centuries almost, because photography, scientific photography has been a great tool for that reason. Even slow fluids also require high frame rates. I already mentioned that, so that's obvious. If you're looking at a millimetric scale, thousands of frames per second is a typical requirement for the kind of flows that you're looking at. If you look at, for example, biological flows, that's typically the kind of frame rate you need anyway. One more thing that I haven't mentioned yet, which is important as well, and we'll see more of that later, is there are other aspects where volume scanning is commonly used in microscopy, of course, for many years as well, and allowing you to scan a volume, for example, on the z-axis, fast with piezoelectric stages, for example. If you combine that with high-speed imaging, that brings you a nice combination that allows you to scan quickly and refresh your scan of the volume at a high refresh frequency. So one more level of velocity that we need to take care of. So I mentioned that bulky cameras have been a problem. Well, this is an example of what it used to look like. You have a bulky camera on a bulky microscope, and that's really not the easiest configuration for a researcher, let alone for an actual product. If you want to turn that into an actual product that sits at least in a lab, in a biomechanical lab for analysis every day, that's a kind of a bulky piece of equipment and also a very expensive piece of kit. So, of course, luckily technology has come to rescue, and we've got much better cameras now, of course, and also much smaller ones. The latest generation being the one you see here with that coin as a reference. So we're getting to a really small scale for high-speed cameras, which is something quite recent and really interesting for our industry, but also for your applications, I'm sure. That's also true for, let's say, specifications in cameras. So pixel rates keep increasing. We've been looking at much higher resolutions. Roughly, if we look at just the pixel rate, so the number of billions of pixels per second that we are capturing, we've been increasing by 120 times in 20 years. That's, the 20 years is interesting, connecting back to Professor Whiteside's presentation. 36 times increase in image resolution available at 1,000 frames per second, 500 times increase in ISO values measuring sensitivity, and 50 to 60 dBs in 20 years as well in terms of dynamic range. So obviously the technology is now very mature, and the number of off-the-shelf image sensors available, including in your smartphone, tells you that we've made a great progress, and we are reaching a stage where we can join the technical revolution of microfluidics and go to the next stage together. Obviously, research has heavily contributed to resolving some of the challenges that I've mentioned, including the road from 2D to 3D, not let alone 4D, and that's true as well for slow confocal microscopy to high-speed confocal imaging, which has become really important as well to make great progress in microfluidics measurements. So starting in 1999 with Maynard for 2D micro PIV, the first validation paper of first PIV micro applications, going through confocal imaging applied to micro PIV, stereo 3D PIV, and then out-of-plane measurements starting to appear to pave the way for 3D measurements, then multiple 2D micro PIV plane using scanning, volume scanning, and then how to turn that into an actual 3-component velocity measurement, and then high-speed confocal imaging, combining the advantages of confocal imaging with high speed. That was a great breakthrough, in my opinion. That's Klein and Posner in 2010, so that's not that old. And then more recently, some smart IDs like microprism mirrors, which allow 3D measurements. So high-speed confocal micro PIV, just very quickly on that side, that's a quick figure showing you what it looks like. There's a nice trick here with a Nipkow disk, which allow you to move basically from slow confocal imaging to fast confocal imaging, and that combines really well with CMOS imaging sensors here. And in that example that was published by Posner in 2009, you've got a 5,000 frames per second case, which is, again, a real breakthrough in high-speed imaging applied to microfluidics. So just to start to wrap up a little bit, what is true in scientific photography is true in microfluidics. We've got a winning combo that is required. We need great imaging optics, and by the way, manufacturers know a thing or two about that, so we can help. Great image sensors and cameras, that's our job, and we're working hard to improve the technology every single day. Great workflow. We talked about simplicity earlier this morning, and I think giving you the easy-to-use tools that you can use at the press of a button, if necessary, when you have to repeat many experiments many times, and giving you something that works out of the box in a kind of plug-and-play approach is important. So knowing about the background of the technology and all the details is good, but at some point you need a tool that you can use daily. So I think a great workflow for these measurement tools is important. And there is a second component that are system integrators, where some companies are teaming up with camera manufacturers to provide you with ready-to-use solutions. You also need great image processing algorithms, and that's where system integrators add a very significant value. And you also need a great measurement data processing and then modeling, and that's how and where we can work all together. So back to what I was saying at the beginning. Again, the type of applications for high-speed imaging in microfluidics, development and validation of microfluidics processes, and real-time use. So just a few to finish, just a few examples of what can be done and what is being done, because all of these images are from published papers. So first, droplets, particles, cells, bubbles, etc., being shaped, mixed, etc., manipulated in general. You've got some nice examples here of bubbles and droplets in that case, sorry, being shaped and generated in a smart way. You've got some examples here of coalescence and how to achieve proper coalescence between different droplets. You've got examples here of observing and manipulating the motion of cells and particles and vesicles in microchannels. And here as well, some very interesting examples of emulsion droplets as they are being mixed. That's obviously also true, and we saw some nice examples also this morning. Sorting applications. If you have a sorting system, if you don't have a high-speed imaging system to check that the sorting is happening properly the way you designed it, that's, well, useless. You need to have one way or another, at least at the development stage, to see that. Another current development that is rather interesting for bioprosthetic applications, this is on the left here, some flow measurements in a new design for a mechanical heart valve. So this is really a way to validate the function of new bioprosthetic devices, and that's true as well as we work in vitro tests to develop new bioprosthetic applications, and that's an example here with flow measurement in blood vessels, lymphatic vessels, sorry. Last but not least, you're all using a number of microchannels in many of your microfluidics devices, and understanding the flow, the nature, and the 3D repartition of your flows in your microchannels is a key to designing an efficient microfluidic device. So you've got a very nice here, very nice 3D representation of a T-mixer, and you can see all the details of what is happening at the micro scale, and that is really remarkable and was quite difficult to imagine a few years back. This is also another example that was obtained with a very, very simple device based on microprism. That's one example I mentioned earlier, where you can get really nice 3D representations of flow, individual particles in 3D inside a microchannel, also remarkable, and something that was really difficult to imagine a few years back, and now achievable with very simple devices. And same thing applies to designing, again, T branches here, where you can see what is exactly happening, and that allows you, of course, to design microfluidics processes that are efficient and achieve the desired objective. So that's the overview that I wanted to present to you about the contributions of high-speed imaging to your applications. And well, if you have specific questions, I encourage you to come and see us on our booth, obviously, and also if you have some questions already, please feel free. Thanks a lot for your attention.